here I would give you an introduction on the QCD topics. And I'm going to start by introducing, give you some history of our understanding of physics and see how we have grown since the, this few hundred years. What do we actually understand more about physics? And here I would introduce first the most complicated subject and most complicated object that we ever know in physics. Is this one. It's nothing. So back in the days, Newton's time, free body problem is not exactly solvable. And then later on, we know two-body quantum mechanics. We also know two-body problem is not exactly solvable. So we go from 3 to 2. And eventually, we learn more. We learn that even one-body problem in electrons, gas, and all this is not exactly solvable because we have so many diagrams and interactions, and then you cannot exactly solve a quantum a condensed matter system like this. And then later on, when we study even more, even zero body is too many. It turns out that no body is already too many. So the so-called many body physics that I want to talk about is actually the same as this object, which is the many body part of the no body, which is the vacuum. It turns out that the more we understand now, the more we cannot solve the problem. And eventually, this vacuum, understanding this vacuum also means, if you understand the so-called non-perturbative vacuum or non-trivial vacuum in more detail, you can also study one body from this and derive all the property of the two body and higher body. Okay, so this is this object that present everything. So one way that we can study this or understand it is to heat it up. So if you heat it up, what happens? Well, you first create a bunch of photons, and then this photon, the temperature would be revealed from the spectrum, the Planck spectrum of the photons, and effectively you know what is the contact. So you get from nothing to something if you heat it up or pump energy into this. And then if you heat it up even further, then you start to produce at temperature about 100 MeV, you start to produce hadrons. You'll get a bunch of pions because they are light, a little bit of kaon because they are heavier, and then the neutron and all this proton and neutron, and even the antiparticle would be created. And this is what happened when you heat it up. Now, what if you heat up even a larger temperature? Then the so-called quarks and gluons inside these hadrons start to talk to each other with some unknown way, not fully understood, but they eventually talk to each other. And eventually, if you go beyond this point, there they have overlap, then maybe, just maybe, that this constituent would come out, and then you basically have a fireball made of this quarks and gluon degrees of freedom, which is what we believe right now to be the fundamental degrees of freedom in QCD. Okay, so this would requires temperature much higher than this 116 MeV. Now, do we know anything about this? It turns out that the number of degrees of freedom, which is just counting the number of gluons and number of quarks in your system, which we can do, right? I mean, there are 3 colors, and then there's number of flavor for the quarks, and there's an effective way to understand it. So let's say you calculate the simplest way to calculate the pressure. The pressure is just the partition function. You take the log and divide it by beta V. Beta is 1 over temperature. Now, you don't need to do this calculation. I'm just telling you that the unit of this is of the order of 1 over energy to the 4. And so the pressure itself goes like energy to the 4. And if you go to extremely high temperature, temperature is the only scale. And so the pressure would be proportional to T to the 4. The prefactor, of course, count the number of degrees of freedom. If you have 1 more gluon, then you have 1 more degrees of freedom. So at high temperature, thermodynamics to pressure should goes like number of degrees of freedom times T to the 4 with some prefactor that I don't care. Right? And then, of course, there will be correction. So if the particle is massive, so then there's another mass scale that comes in, and then it would change this picture. But these are details, okay? So you basically, the number of effective massless degrees of freedom in this one that you have here, you have massive degrees of freedom, and eventually you becomes massless degrees of freedom, eventually increase as a function of temperature, just the degrees of freedom. And so helps you to understand on the lattice QCD calculation, for example, you calculate P over T to the 4. So effectively, you're counting the degrees of freedom. And you see at low temperature, it's very small number. And eventually, it saturates into a constant number. And that constant number exactly counting the degrees of freedom. So if you want evidence for change of degrees of freedom, this graph, roughly speaking, support this picture that eventually you're just counting the number of quarks and gluons in the system, at least for very high temperature. And there's a lot of detail that I would not talk about, but this is how you understand this picture. This is how you at least burn the vacuum and what happened. Now, the structure of the vacuum is not totally understood. It's still an open problem, but this is our guess right now. I mean, there's many versions of this, and most likely this phase diagram is no longer valid as of now, or even in 5 years, maybe it's proven totally wrong. But this is what we are expected, okay? So this is plotted as a function of temperature and density. So at low density, like our everyday life, we are here at low temperature, we see hadrons, basically your proton. You are made up of proton and your pion and all this. These are basically the hadrons. And then if you increase the temperature, then your gas get excited. This is the picture I just showed you. And then you can move along the temperature side. And the latest heavy ion accelerator, AHC, or even REG would explore the phase diagram along the temperature direction by trying to collide ions together, okay? You can also go to high density, then you expect that eventually you see a line here. This line signifies that the expected, you're expected to find hadrons to become this quarks, free quarks and gluon state. And then crossing through a line means there would be a phase transition. This is what we expect. However, we would not expect such a case in the normal low density case here. So eventually you go from continuous transitions to having a line here. So somewhere in between there is expected point at which the phase transition changed from first order into a crossover. This is the second order endpoint for chiral physics, and this is called a critical endpoint. And a lot of experimental effort and theoretical effort is trying to in search of this point and find out what's going on. And so far we have not had that yet. And so we need to go to higher density in order to explore the physics of this one. But this is what we expect for a phase diagram. Now, this is very simple phase diagram, of course, but if you look at even your everyday life water, it's actually much more complicated. Now, this here is the phase diagram of water, pressure here, temperature here. So we are in standard, we are at atmospheric pressure. This is how you boil the water. You boil from gas at fixed pressure. You increase the temperature, and when you reach 100 degrees, then it becomes gas. This is your everyday life experience in this. And, you know, but then you probably have not seen, actually, much less have been seen about this temperature versus entropy graph. So this is the same for water. So eventually, if you increase the temperature, then there would be an instability region like this. And then you follow this line here, you have a jump, and then eventually you go to the gas phase. If you tilt your head, then you see there's a jump in the entropy, right? From low temperature, have a jump, and this, and that's the usual graph that you would expect also in this phase here. When I plot this along this line, that increase the temperature, there will be a jump. This is revealed as this, following on this line. So even water can be actually water is complicated. So this has to be modified eventually for our QCD phase diagram. So how are we going to study QCD phase diagram? With what tools we want to study this hot and dense system, okay, of QCD? Well, one way is to ask the universe to bang again. So we can do this again and again, and eventually we can study in detail what's going on with the particle production and all this. Another way is, of course, you can go to study some cold object at high density in this time. For example, neutron star and neutron star mergers, and even black hole. And then you can study the corresponding lower side of this side. Then you can study low temperature, high density. Or we can build an accelerator. This is the heavy ion program that I will talk about. So let's briefly look at early universe. So the universe is this is what we tell our kids now. So you start with a Big Bang. This slope is very steep because it's an inflation, and eventually the universe expands. As it expands, the temperature cools down from very hot to very cold. And there's several interesting points. For example, the cosmic microwave background comes from the last scattering surface, and this is what you see if the photon spectrum right now come from this stage. Anything before, you would have no chance to know because it's milky. Now, if you go to earlier universe, temperature increase, this line, for example, at something around here. So that would be the possible phase transition from quarks and gluon into hadron state. And that is the line that I just showed you is here. And if you go to even earlier one, then the temperature reach the mass of the W boson, then you can even restore electroweak symmetry. And then there will be even earlier phase transition to study this. And right now, the energy of the LHC is way beyond this point, way higher. However, to create a thermal medium of such thing require a lot of effort. So it's not just about the energy, it's about forming the system. So this is the, what I say, last scattering surface, and this is the deconfinement. This is the object of study that we are in this talk. We are interested in QCD and its QCD deconfinement phase transitions happening at temperature around 170 MeV. This is the typical temperature. So we cannot ask it to bang again and study, and we do not want to talk about dense matter now. Let's look at how to understand heavy ion collision. This is, theorist toy, but experimentally, of course, there's a whole program involved, which I am not the one who can actually explain everything. But let me try to give you a theorist view on this subject. Now, if you simply shoot two nucleons together, or even heavy nucleus, okay, at low energy, basically this thing would touch each other. And then effectively, then after they touch each other, then they would go away. And the remaining stuff, because, imagine I go through you and then we friction or, we rub each other. And then, of course, we get a little bit excited, depending on your attitude, or you get angry. So effectively, this thing is at slightly higher temperature or excited state. So it gets hot. And then what does it do? So the remnant of this heavy atom or nucleus would start to vomit neutron or photons. And then you fit a thermal distribution of the particle that you collect all this, and then you get temperature. And such temperature is this temperature that I show here. And if you increase the energy a little bit, then you get more excited, more photons and more neutrons coming out from the fission. And then you can actually measure the temperature of this one as a function of energy per nucleon. And this is the graph you see here. And these are the experimental data. You see that eventually the temperature would increase, and then suddenly it no longer increase even if you increase the energy. And then it would increase again here. So this is the so-called liquid gas phase transition of the nucleus. It happened at around 4 GeV or 4 or 5 MeV mega electron volt. Okay, and so if you tilt your head again, you see the energy as a function of temperature would have a jump if you go high. This is a first order phase transition like this, and this is how you understand, relatively low energy glancing through like heavy ion collisions. Now, what happens if you increase further the energy and make it more, center? And then you would excite a lot of stuff inside, and it's excited so that you start with a lot of nucleons, you end up with new particle. So something get in, and then the things that get out is completely not in the beginning. So basically, the pictures that we have here is that you excite the vacuum, and the vacuum start to vomit a lot of particles coming out of this. And these particles, it turns out that it would follow some kind of thermal distribution. And that thermal distribution would tell you what is the temperature of the matter that is being created. Okay, so we are not using the same method we have here, but the temperature that is determined from this, you can see a single temperature and the corresponding chemical potential would be allowed to fit all the particles that you see from this experiment. And eventually that is how we understand the temperature of the final fireball is of the order of 155 MeV that we have here. How do I know that the baryon chemical potential is 0? You can look at the number of proton is the same as number of antiproton. So you create the same number of proton and antiproton, effectively the chemical potential would be 0 because the net density is 0. Okay, and then if you look at this graph, roughly speaking, in these situations, the number of pion compared to proton is of the order of 15. So how do you study this physics? You should be good at pion physics, because for every nucleon that you see, you have to deal with 15 more pions surrounding it on average. Okay, so pion-nucleon interaction becomes very important to understand this physics. In fact, I spent a few years of my life trying to correct this point. You see that the theoretical prediction is slightly about this. You see here. So the data is slightly about this, and that is about 30%. Remember, this is a log plot. So you can put in better physics to explain even fine differences like this, okay, by using non-hadronic interactions. But this is topics for the other day. So this is how we know the temperature of the system. Now, can we change the temperature? We have a phase diagram, right? So how do we go? We would be here, around here at low density, actually 0 density, because the number of proton is the same as number of antiproton. It turns out that in heavy ion collision, if you decrease the energy, if you do not go to such a high collision energy, then effectively you pump energy into the vacuum, the pion and the proton that are born would still see the original nucleus around you. Okay, so when you pump it very high energy, then it doesn't matter. The original things doesn't matter. But if you put it in very low energy, then when you're born, you still see the guys around you, and which is a lot of nucleon. Okay, because you are in the heavy ion collisions, and so you effectively feel a slightly larger density side. And it turns out that this is the correct way to understand. If you decrease the collision energy, the baryon density would increase. You will see more proton than antiproton, and you would not see the number of pion being larger than the number of proton. In fact, this ratio inverted for the typical experimental situation. The number of proton compared to pion is of the order of 100. You most likely have 100 proton. You almost have no pion in this case. So in going from here is pion physics. In going to here, that would be nucleon-nucleon interaction. To study this, you need a potential model, or study nucleon-nucleon interaction. Instead of here, you study pion-nucleon interaction. So this is how we walk around this phase diagram. This is called beam energy scan with experimental tools like heavy ion collisions. So this is a simulation. This is more like the first scenario that I talked about. You have 2 heavy ion collisions, and then they create all kinds of particles. You see the smallest particle get created most because they are lightest. So you pump in a lot of energy. After thermally produced, then the lightest would win. The lightest actually are pion. But you see also they create some kind of exchange and all these baryons and even antiparticles. And if you count the number here, you would get the graph that I just showed before. Okay. So I told you about that you can fit all this, and you can even improve this fit further. This is the temperature that we see. So this is amazing that as a function of temperature, as a collision energy, as I told you, the higher the energy, then it would correspond to a temperature 155 you have here. If you lower the collision energy, you effectively go to lower temperature, but higher chemical potential that I show here. The system would become baryon rich in this case, okay, if you go to lower energy. Now it's shocking that the temperature, like saturate, do not increase any further. But this is easy to explain, because if you throw 2 water together, you detect water. What is the highest temperature that you ever can detect? It will be 100 degrees because it's water. Because it goes from gas, somehow you detect as water. And so this point is not about phase transition, but actually rather the maximum temperature that you will ever get for effective hadrons. But there's of course a lot of gas or whatever, but the saturation is very clean, easy here. If you even go to higher collision energy, you would end up with this temperature that you see here.
So you may
yeah.
Question.
Yeah.
In some previous pages, you have shown that in the low energy nuclear collision, you have a transition from the liquid state and the vapor state.
Yeah.
And do you see such kind of behavior in this
here?
graph? Yes.
No, it is not yet so dense yet. So at this point, the saturation, the effective baryon density is not so, it's not so high yet. roughly speaking, the number here is around maybe 0.5, saturation density 0.8, but people are looking at that. If you go to even lower, you can. But at low temperature and no chemical potential, you should not trust this model because there's so much in the nuclear physics that you may not be thermal. You can argue about small system effect. So it's full of, ambiguity. Yeah, sure. Would look like a first order phase transition. Well, actually, one should not say so because this temperature is just the temperature you used for the feed. This is called freeze out temperature. In principle, it is related to the highest temperature you can reach. And one may be tempted because the temperature is almost like the chiral temperature, but it is not the same. In principle, the chiral temperature is higher than freeze out because that's at the point you have, right? So it can only be higher. So it set up the bar of the lowest limit for the chiral temperature. Okay, so the physics is a little bit different when you define it. Yeah. So this is hadron yield. So you collide this, and then the vacuum vomit all these particles. You detect them, feed the temperature. That's how you learn about the vacuum, right? There's a more clever way to study this. For example, if you look at the sun, okay, you see the surface temperature. These are the photons, right? But this is not the only thing you can study. There's something deep inside which gives neutrino, and that you get detected. And what does this thing teach you? This thing teach you about the nuclear physics inside the sun, which is the fusion case, right? And so you can imagine these things actually go out of the fireball unscathed, right? There's also something like this have heavy ion collisions. Of course, the pion and hadrons are inside and where you detect them. But there's something that can get out of this in the earlier stage that would go beyond my 150 something temperature. And in this case, these are the particles that does not interact strongly. These are, for example, the photons and the leptons. And so by looking at the leptons and this and guessing the spectrum, you can learn something about the earlier stage of the fireball instead of the last stage. Now, for example, if you're very smart to analyze the neutrino here, you would find the neutrino spectrum like this. And in fact, from looking at this graph experimentally, these are the neutrino flux at each energy. If you look at lines, if you see lines, which mean neutrino comes in with a definite energy, it means if you study enough particle physics or decay physics, it means it's a two-body decay. When you see a whole spectrum here, it would mean that the energy is being shared among all these particles. It would mean it's at least three-body decay or Dallas decay. And that you can actually infer from this kind of a model that we have, network model, to infer the spectrum of neutrino. Now, imagine if you do something like this for the hadrons, for the leptons, and the photon. That would be very nice. But this has not been completely done yet. But this gives you a chance to go to earlier days, earlier temperature, and that would be something for you to think about if you're interested in this topic. Okay, so the last tool for analyzing compositions of hadrons would be related to lattice QCD. You would think that, how can numerical simulation can help here, right? Because it's a number of proton is not a things that they can calculate in lattice QCD. It's not a conserved quantity, okay? Only baryon, charge, and strangeness are conserved quantum number, but not the number of pion and the number of proton. For that, you need a model. And so it turns out that even in lattice QCD, you can understand the composition of the fireball via something called fluctuations. Now, fluctuation is like you have a system, you turn on a little bit of this chemical potential that I have here. It can even be sometimes mass of the quark, okay? And then you change the system a little bit and change it back. And this is the standard linear response. And if you study the second derivative of this partition function, you will be able to screen out, for example, if you take the number of baryon here, then the particle who do not have baryon charge will be left out. And so effectively, by very smartly playing with this baryon and all this charge, you can decide how many of this thermodynamic pressure come from the proton, how many of this come from the pion. And indeed, these require the high school mathematics of taking two derivatives, actually. But when it goes to large scale simulation, it's actually not so simple. However, in the lattice QCD, you are computing correlation function, which is a lot harder. So for theorists, we just take derivative, but for lattice QCD people, they have to study correlators. And they are the same thing. That's the beautiful things. And then you can see, for example, the hadron resonance gas model that I just give you, just a thermal distribution actually can explain the number of baryon inside the lattice system that I have here. And more detail, I would not go through. You can, for example, look at baryon charge correlator to fish out the number of proton. And it turns out that this is related to the number of proton. So the predictions of your model can be related to lattice QCD and can also relate to the heavy ion collision that you see. And similarly, you can do it for strangeness. But this would be a topic that I would not do here. And then, of course, if you take the ratios between the number of lambda, proton to lambda, you would have some nice prediction, which is usually very difficult to get from standard model. Okay. So that concludes basically the introduction part of the stuff. And then we go back to theory. I actually promised a theory talk, and now in the second sections, I would talk about how do theorists understand the phenomena that we just discussed. Okay. So we have the tools to play with, but we still have theory to analyze. And the theory I want to analyze is QCD, which can be written in a single line. This is very easy to write, right? You know the QCD Lagrangian, there's nothing else, okay? And QCD is a renormalizable theory. It stands on its own. If you calculate it, it should get answer. And that is what we mean by understanding physics. Nowadays, some people used to forget that because we get used to solving effective model and all this, which is useful. However, one have to remember, in the end, you want to connect that to the fundamental degrees of freedom in order to what it means by understanding it, okay? Now, so the Lagrangian basically tells you that you have quarks interact, quark propagator, and quark would interact with the gluon and the gluon propagator. This is nothing. This is like QED, right? So you have a photon, you would have photon interact with the fermion and then the fermion propagator, like the usual case. Now, except in QCD, there's two more terms that the photon itself, you can imagine photon does not have charge, and that's why it does not interact. This is gauge theory. It's all about charge. However, in QCD, the charge is different. The symmetry group is SU3, and so effectively, gluon also can have charge, okay? And so the fact that gluon has charge means they can talk to themselves, and that's why there would be self-interaction of gluon. And of course, the quark also have charge, in this case, the color charge, and it would interact with the gluon. And so this mess, if you can do this, that would be complete solution of the theory. But right now, we cannot do this yet, okay? And no one have been able to do this, except in lattice simulation at some specific regime, you can do actual simulations to understand that. But it's not solving for Green's function, this kind of solving it. Now you see that this extra term, this is the standard term that you observe in QED also. But this term that you see here are self-interactions of gluon, okay? And that is very specific to QCD. And the idea is that you do not really see gluon nor quarks getting out of the system, okay? And this is the phenomena of confinement. And basically, it should come and it should be derivable from what I show here. So anything you ask about QCD should be derived from this page, okay? So there's many ways to understand confinement, and actually we do not really fully understand it, to be honest. It's difficult to say what is confinement, but it's easy to see, to say what it is not, okay? For example, the common notion that you cannot find free quark is not confinement in a sense. In a sense, what you're saying is that you can't find it, but why you can't find it? So if nature would give you a scalar particle that binds to it, that is colored scalar, which binds to a quark, then it is colorless, but it would have fractional quantum number and whatnot, and we do not see it. And if you say free quark means, no free quark mean confinement is just accidentally, we don't have such scalar. It explains nothing about the color force. So it has to be related to color force. You can say non-abelian gauge theory automatically leads to confinement. This is not true. The weak interaction is SU2. It's also non-abelian. Non-abelian means that such term would exist. but this is not true because the weak interaction is also 1 billion. So one actually want to discuss confinement, is better to use, for example, the long range interactions between two constituents. It grows, the force is constant if you go to far distance. So that would be a way to understand confinement as the existence of long range interaction between quarks or gluons. Okay? So that is the picture. So if you have, let's say, an electric charge, attractive force, then you will see the force actually will drop as a function of distance, and that's why you can see them far apart when when they don't touch each other. However, with confinement force, the force actually stays constant. Okay, you may be used to the linear potential. If you take the derivative of the potential, this gives you the force, and that's why the force should be a constant. And then you would never be able to separate them. Remember, it's not harmonic. Harmonic would be the force would be linear. Okay, so it's not a spring, but it's a string, right? So this is the picture, and if you do some lattice simulation, you see that the energy density between a quark and anti-quark seems to be the strongest around this one, and this is the energy content between 3 quarks here, and it seems that the energy is among all these quarks, and then so this seems to be supporting these string pictures. Okay, so it would not decrease as a function, but more like increase. Now there's more. I say gluon can bind themselves, and so there is actually possibility that the gluon all the way just bind by themselves to form colorless object. And so, for example, if you analyze the Dallas decay of the 3 pion, and then you pick up 2 pion at one time, and then you may find some band and structure from the Dallas decay, and that would be your indication for such a glue ball that you observe. This is very old experiment, but some object may be proposed to exist. Anyway, even this time when I visit here, we are having heated debate about how to understand this state. So this story is unfinished, and hopefully we get something by even today. So you want to understand periodic table, there must be hopefully some chemists around. And what is so if you ask yourself what is so periodic about periodic table, it's actually this, right? So the periodicity comes from the fact that you have quantum mechanical interactions inside, and then it has to follow some, due to quantum mechanics and the force of QED, then effectively you would have this arrangement that comes in, like the principal quantum number and all this. Now, eventually we learn that, atom is no longer very simplest object, and it has all the structure inside. And at the end, we end up with gauge theory, that basically charge is exchanged via gauge boson, which in this case is the photon. And then in general, we exchange particle for the gauge bosons. It can be even be massive. So this, if you're smart, one should be able to infer from this, all this physics, and propose this. And this is how we understand it, okay? Now, can we do this? There's a lot of hadrons that we see. And in principle, you should be able to build it using the basic principle of gluons and all this interaction among quarks and gluon, and even glue ball. And so there are some symmetry, which is related to flavor and color of the symmetry of the system, which you can understand the many hadrons that you see here, okay? So the challenge I would give you is that, can you actually get from such kind of potential, or the confinement potential, and all these color principles that you have and flavor principle, can you have a good descriptions of the hadron spectrum from this, and how QCD forces actually manifest from this? And this is one way to understand how confinement works. There's also vacuum, and this is a simulation for the vacuum. It is very complicated, energy being create all the time, and then you would have, on average, of course, the vacuum quantum number is 0, but as a function of time, it keeps fluctuating. If you now start to put stuff into it, then it starts to interact with the stuff inside. So vacuum is not nothing, and then it will start to behave like abnormally. For example,
so what is being displayed in this model?
This is the energy density of the pure gluon system. It's in the simulation as a function of time.
So like you would have in the global, right?
Yeah, or you can associate nums of this as a nums of energy density. Yeah. To get the glue ball, you really need to fish out the quantum number. That get a little bit harder. So if you put in quark and anti-quark in the system, you pull it apart, of course, the energy density or energy would increase, and keep on increasing. But if you put in quarks inside, this is pure gauge system, there's no quarks inside. But the moment you put in quarks, this picture is that you can create a pair of quark and anti-quark in the system, and then it gets split into the two. So this is not the confinement. This is string breaking. The fact that you talk about string is confinement. So string breaking means that you have a string. And so your actual observation is actually it increase, and then it will follow here. That will be the ground state. And it is very difficult to study the energy surface here. Okay. And so this is not the potential, remember. The quark potential can still be confining if you're able to follow the line over here. It's just string breaking have to be dealt with for the real QCD system. So for the pure gauge system, at least we can study also it as a function of temperature. This graph shows you at low temperature, this is the free energy. So the potential between the quark effectively the same I show here. This is at 0 temperature. If you increase the temperature, you will find that you increase the temperature effectively, the potential goes down. This is pure gauge. There's nothing to break the string. The gluon cannot break the string. And then if you increase beyond some critical temperature, then the string tension goes away. It's flat. So this is how you understand going from something to a confined phase to a deconfined phase. And this is first order phase transition because you have some non-zero values here, and then you suddenly jump to 0. Okay. And so this is lattice data from the Bielefeld group, and you can define an order parameter for the deconfinement phase transitions by constructing an object like this. So here's how you understand it. If the free energy at long distance is infinite here, then this is infinity, and so this would be 0. So this number would be 0 if you're in the confined phase. However, this potential becomes a constant if you increase the temperature, and so that would be a non-zero value. So when it is 0, it's confined. When it is not 0, it's deconfined. And myself and also in collaboration with the Bielefeld group has extracted this quantity from the lattice, and you see that it was 0, 0, 0, and at the transition temperature, it has kind of a jump structure, and at this. Of course, at finite volume, you have to deal with this situation that you have to extrapolate to infinite volume, but it's actually known that it is weak order phase transition that you see here. And this is TC. You don't know what is TC. You determine it separately, which is around 270 MeV, much higher than the 160 I told you, because it's a pure gauge system. The pure gauge system means you have only gluons. Okay. So you have an order parameter that I show you here that does not respect the symmetry, and so can be used. It would be 0 if it is confined, non-zero if it is not confined. You can also associate a symmetry group of the transformations. It turns out it is set-free symmetry group, for the one who is interested in the mathematics of it. Now, if it is SU3, there's a set-free subgroup there. Then you can consider the following, that if your Polyakov loop here, or the order parameter is complex, okay? You can study both the real direction and imaginary direction. You can study the fluctuation along the real and imaginary part, okay? So usually the order parameter is real, but you can, for the SU3 or set3, this has to be complex. And so you have a real and imaginary. Another way to understand it actually is that, that we can do, but it has a real and imaginary part, and you can also study the fluctuations of the order parameter as a as an order parameter, because order parameter is not unique. If you have L as an order parameter, L squared is also an order parameter. And so you can study this fluctuation, and this indeed is also computed on the lattice, and they show very different structure. One is much larger than the other, and you can build a model. Actually, this is what happened. Below the critical temperature, you have a circular shape, and the order parameter, the minimum is here, and so the vacuum stay here. And if you move around the real and the imaginary direction, it's an almost circular ball because you are at the middle. So the two fluctuations actually is similar in this case. However, above TC, then you have a spontaneous breaking of this symmetry then you see that the fluctuation along this side is so much smaller than the fluctuation along the real directions. And that's why you will have huge difference below and above TC. I don't have to talk about the location of the minimum. I just use the curvature to understand this. The physics reason behind actually can be related to the group structure, that for the SU3 group, for the Z3 group, there's two generator for the Cartan algebra, and these two correspond to the real and the imaginary part of the order parameter. But there's some, more in-depth mathematics with this, but this is not the place for this, I guess. Anyway, if you take the ratio of the curvature here, you can calculate on the lattice, and indeed you get something that is around 160. It goes from unity to very small number that you see here. This is actually the evidence of the deconfinement in the lattice QCD in the full system. Yeah. This thing only talk about the gluon, has nothing to do with chiral physics. Also in chiral physics, it is around this temperature. So we believe the confinement and chiral transition happens in similar temperature, at least for the pure of the zero chemical potential language. Okay. So let me use the remaining time to quickly go through chiral symmetry and the modeling aspect. Okay. So chiral symmetry explain, of course, the mass of U, but it's not the mass of the, the Higgs boson do not explain the mass of the universe. Actually, the Higgs boson explain the mass of the W boson, not the mass of fermion. It's explain it a little bit. But most of the mass is explained by actually QCD or chiral symmetry. So the story runs like this. A proton is made up of 3 quarks, is 900 MeV, you divide it by 3, then the pion is made of a quark anti-quark, so you expect divided by 3 to be 300, the pion should be 600 MeV. But it turns out that the quark is a few MeV only, it's not 300, and the pion is 140, so nothing works, right? And in order to understand that, it turns out that if the quark mass is absolutely 0, the current quark mass, then QCD contains a extra symmetry, which is called chiral symmetry. And this symmetry is hidden. This is why it is called spontaneously broken. And then it means that there is a binding of the quark and anti-quark, and this effectively would generate the mass for the fermion. And then you can actually understand this mass scale is around 300. What's more, chiral symmetry would give you the pion here is not just QQ bar state. However, it is actually a Goldstone boson case. And this has a very weird situation that the mass of the system is not the sum of the masses, but actually it's the square of this goes like linear. Generally, you expect mass of pion to be linear with the mass of the system. However, if it is Goldstone boson, this factor is a square root. So this, of course, represents the Nobel Prize in physics to understand this system. And effectively, you can understand this via this chiral model. If you go along these directions, it's difficult. That's why it's massive. If you go along this direction, it's very easy. So you see from the curvature, like what I showed before for the confinement, from the curvature of the potential, you can tell the mass of pion is 0 because its shape is like that. Along this direction, you take energy to create such an excitation. And so the direction along this direction and this direction is very different because the symmetry is spontaneously broken. Why there is a symmetry? Because there's nothing to tell you which direction it would go. The rotational symmetry is intact here. However, the system accidentally go to a certain minimum and you will have this behavior. That is what it means by the symmetry being spontaneously broken. Okay, it turns out that in the lattice, you have chiral condensate going down, and then the Polyakov loop going up. These are the two order parameters studying chiral physics in the confinement. It turns out that in effective model, you can also give something like this. Okay, so I guess I'm at the end of the talk. Do I have still 5 minutes?
Yeah, of course.
Okay. So the last topic is something that is more like front and unknown. First, because confinement is unsolved problem. If I have solved confinement, I would have claimed the money. However, confinement, essentially to describe confinement in the theory, you have to fix the gauge because you have to talk about the gluon. And in order to solve for the Green's function, you have to tell me which gauge you are in. Unfortunately, the description is always gauge dependent. Okay. And in Coulomb gauge, there's something special. And why do I choose Coulomb gauge? Because in your QED, let's say you have a photon, you are used to Coulomb potential. And this gauge is the only gauge at which you can derive a potential. In quantum field theory, you never have a potential in other gauge. Only in a potential mean is instantaneous exchange, okay? Which is derived from the original Lagrangian, not assumed, okay? And so in QED, you can do Coulomb gauge and you can explicitly define a Coulomb potential, which basically follow Gauss law. If you recognize this is just the Gauss law, A0 is just the zero component, which is the electrostatic potential you have. And the electrostatic potential would give you 1 over gradient square, which is the 1 over R potential that you observe. This is all good. In QCD, you can do similar things, and you can show that the corresponding potential becomes this. If what I said is correct, when you calculate this, you instead of 1 over R, you should get the linear potential. And it turns out that a complicated calculation actually shows that it is true. So what is the ingredient of confinement in this case? Well, it turns out that because of the covariant derivative here, this is due to non-abelian nature, then this thing is not gradient, but have an extra A in it. So it depends on the field, the gluon field, because of the non-abelian interaction. And then you would actually have to take care of that. And this dependence would make everything different. And then it would enhance the infrared, which is the long distance behavior. And this is in this picture, which causes confinement. Okay, so these are some details. And then you can also explain, this is the confinement for the quarks, for the gluons. And the same mechanism actually.
So, sorry, Janet, in the previous page, you have wrote the confinement potential, but is this that is the result, or you got this result from this analysis?
Yeah, these are points are lattice, and the lines is the result from this analysis.
And can I ask how did you get the confinement part? I mean, linear part.
It's basically solving for solutions of this operator. This thing would satisfy a Dyson equation, and it would be solved. There's a lot of details that I skipped, but we can discuss here. So basically, the key ingredient in big summary is that there's an infrared enhancement due to the presence of the gluon field in this operator, which is only happen in non-abelian gauge. And with this, you have a non-trivial vacuum structure where the gluon is already in the vacuum. You do the Hartree-Fock-Bokili-Bok assumptions, and you solve this equation, and then you will find that at long distance, it gets enhanced. This is the summary of the story, of course. With the same thing, you can also discuss the quark confinement. It turns out it's the same things. So the quark and gluon confined under the same manner, because in QCD, there's nothing to distinguish between the two, okay? It's just gluon exchange that causes it, okay? And so as it is, then you can find something that, you know, the quarks are indeed infinitely massive infrared divergence, and that's why you don't see it. However, you can define some mass function, and the condensate that we observe is indeed have chiral symmetry in it, and then you can get the chiral symmetry in the vacuum also. And also you can derive pion and Gell-Mann-Ostrander relations. So I would skip the details. They are not necessary, but you know they are there. You can ask if you want. So basically, you can get the gluon to confine, and then you can solve the Dyson equation that I show here. And then you can see the mass of pion as a function of quark mass is that it's 0 because it's a Goldstone boson, and then it goes like that. And this is the mass function of the quark. You see that at large momentum, it is 0 or go back to the constituent quark mass. This is something called asymptotic freedom of QCD, that the mass of the functions goes down, and then it's just perturbative in this region. And then this non-perturbative physics is all contained at the low momentum part of the system. Now, this is, of course, too detailed to discuss. And this actually is my PhD work, who try to implement an improvement of the ring approximation to the potential to understand the phase diagram and understanding first order phase transitions. Okay? So the fact that it is possible is something that I want to show you, at least in this case. So we are working towards, me and my student is actually working towards deriving the QCD in Coulomb, the phase diagram of QCD in Coulomb gauge, really picking all of this together. And it is funny that it is not even done. We don't, you know, this is how much we don't know about QCD phase diagram. Maybe just 1 minute for dance manner. Sorry.
Yeah,
So
so you can.
mhm. So there's another motivation to study QCD because we want to understand dense matter, and dense matter is difficult because first, no one actually understand the equation of state at very high density. These are poorly known by physics because scattering experiment only tells us at low density. Okay, and the density that I probe with heavy ion collision is not that high. Okay. However, you want to understand the core of the neutron star to understand the hyperon content and how about the stiffness of the equation of state. It turns out that modeling and understanding this is theoretically understanding is very important. And Lattice QCD cannot help you here because of the sign problem. So the first principle simulation is off the table. Okay, and so we are interested in this region, low temperature, high density. And what is new? So the core of the neutron star, you can have many speculation, but I offer so it also changed the way the neutron star masses would be observed as a function of its radius. The two solar mass is very difficult limit for standard equation of state to have reached. But what I want to share is that how it relates to what I just described. At low density, you can deal with pion. But if you go to denser and denser medium, as I told you, you should study nuclear. Okay, and indeed, the anti-nucleon can enter, and then you can have all this picture. And the physics of this is low density. Going to high density is already very difficult because this is poorly known. Okay, and in terms of QCD, is even worse. And also, no one really know what happened to gluons inside those medium because no one actually interested in gluon. So these are some of the open problems. And you actually, most of the modeling is very poor. And this is the speed of sound that you see here. The expected values is 1/3 here at very high energy density because this is a requirement from theorists. And you see the color banding is just, what happens in most models, all the model existing, okay? And then you see that they change the behavior, but most of them actually satisfy this 1/3 and all this. And if you put the simplest model that you would ever do, which is the Nambu-Jonas-Lasinio model, you would actually fail to capture this 1/3. Okay, it turns out that dynamical effect, which is the distance behavior of the potential between the quark, is very important. And once you have the gluon exchange here, you can really solve this problem. It would reach the 1/3 in a very satisfactory way. So the input of good physics is relevant. Okay, and so you have to actually to build a better model than this. And this type of model is actually 90% of this one that I showed here. So this is how poorly we know about this model. Okay, this I can skip. And so understanding this is also equation of state is important to understand how neutron star, for example, cool. Which kind of diagram would be most important at dense matter, and this kind of question that you can actually understand. So this, I think I still in the time from you, but thanks for your attention.
Thank you very much for this and very comprehensive talk. And I think he talked a lot, many things about hadron physics, and of course he presented his own power recently. But anyway, so I believe many people are convinced with the interesting things about this topic. And now we are open for the question and discussion time. So if you have any questions, you can ask in the Q&A. And we welcome some naive questions from non-expert people. Not only from this, you are the expert, but we are welcoming some simple and naive questions from non-experts, people and students.
Yeah, every question would be appreciated. It really helps a lot. So when I give the talk, people ask me questions, then I fill out usually the answer to this. So actually what you see here is a lot of questions. Yeah.
So you mentioned you had some engaged discussions in relation to gluons. I assume maybe models that have not topology nature as well. Well, is it in here?
Yeah, so basically Shikihiro discussions how to model this state, whether this is a QQ bar state or the glue, the usual constituent quark model. So what is the nature of this and how it appears? Because there's some I cannot say that, right? The data, so better not. There seems to be some experimental news about this. So that is why that was the discussion about. But the nature, we have not actually touched on topological aspect. Yeah. And how the topology would help, actually, maybe you can explain.
Well, but I think the way models that would describe blue balls as some kind of siliconic model.
Okay.
And then those would be tight knots, and then depending on the knot invariant, the length of the tube would be different, which would be proportional to energy. And people were able to fit the experimental data with essentially models of this kind. So anyway, we will then.
Yeah, then we should discuss, because I am definitely not knowing not an expert on this kind of things.
Yeah, so
we are building hadronic model, but you know.
in the theory system, Canada, I believe, is one of the proposals to this model.
Yeah.
And actually, the blue ball is one of our topics which we are discussing in while it is staying here, and yeah, we are going to develop discussions, and I hope we could say something becoming the future.
The problem is that there's something that, you know, experiment we cannot reveal, right? So,
Yeah. So,
but you can ask.
so I think he showed some graph about the vacuum. Can you show me the fluctuation of the vacuum in the
Pure gauge.
pure gauge, and
I believe it's later.
maybe in the later part. But it's somehow related to the this one. This somehow related to the blue ball structure, but more precisely to say, this is not really blue ball.
It is not.
It's a kind of fluctuation of gluon still. And it's called the instant actually in the specific name. But anyway, the important point is that our vacuum is always fluctuating. Our vacuum is not constant. That's why we can create many different kinds of particles from the vacuum.
Yeah, so that's why this thing can happen.
Yeah, and this is the one of nature. And can I ask you one thing? Because you mentioned the chiral symmetry, but in what sense are you using this terminology? Because for example, we have the left hand side and the right hand side, left hand, right hand, and they are called chiral each other. And in the particle physics, especially in this Pok physics, in which sense do you use the chiral symmetry?
So in this case, it's basically the Lagrangian of QCD that I show here. If you enforce the chiral rotation, which is essentially left-right, but we use slightly different language. You use the gamma 5, and so there is a definite way to rotate chiral symmetry, rotate quarks under chiral symmetry, and this Lagrangian is chiral symmetric. And so that's why if the vacuum has spontaneous chiral symmetry breaking, it would have it, and it does because mass is dynamically generated.
So your Pok have
Chiral.
Right hand side and left hand component.
Yeah, of course,
So
because it's the gamma 5. We combine them when we plot them, yes.
Yeah.
But the key aspect is that the mass here, you see, at very low momentum is higher than you expect from the current quark mass. And so chiral symmetry is dynamically restored even at vacuum at t equals 0 at high momentum, because you have to respect the asymptotic freedom, which says that at largest energy, QCD is perturbative, and chiral symmetry is not, you know, it is restored at highest energy. And so you really see this beautifully here.
So yeah, that means at the low energy part, small p, the left hand side and right hand side are not independent.
Yeah.
They are connected each other in a vacuum, but the high energy they are disconnected.
Which is shown by the condensate also. The condensate is non-zero at low momentum.
So we have another question. And of course, we are welcome for this part of the people.
Even if not, if you write down something, please contact me. I really appreciate any, question that you may have.
Do you have any questions from Zoom? No, nothing. So may I ask one thing?
Sure.
You have shown a nice figure about the evolution of the universe in the first few pages.
Yeah.
And you emphasize that we are concerned with some specific period of our universe. And here is a place heavy ion collisions and the QCD matters coming in this game. And my question is, okay, you mentioned about the heavy ion collisions on the Earth, Earth as the accelerator physics.
Yeah.
But I'd like to know, when we observe the universe, then how can we get some information about this kind of phase transition from the cosmological observation about this hadron transition?
That is indeed very difficult. From the electromagnetic wave or that kind of the light or whatever, the earliest you see is much later, which is the last scattering surface. So which would be here. Before that, the universe is milky. So even if there's signal, it would not get out. So you want to think of something that can escape the fireball. And I may guess gravitational wave, but it would be difficult.
Yeah.
But I mean, and then any remnant of this, you can get it from maybe the distribution of matter, but even that is not so early. So I would say it is quite difficult to get directly from the early universe data. But from neutron star mergers, you actually can get something, because then the density is of the order of field saturation density, or 1 or 2, but the temperature is of the order of 50 or 40 or 30 MeV. So then you actually have some chance of looking.
Okay.
Yeah.
That's nice.
Yeah.
Okay. Do you have any?
Well, just kind of because we are in the Institute focused on nodes, and there are these models which they have been around from 2005. The proponents, as I mentioned, are Clampert, Moni, and also here in Japan, also there are those doing this work. So, for example, Hondo. And so I'm reading here just the titles from some of these articles. Global mass from quantized non-solitons and globin red. Then not energies and global spectrum. So there are a series of articles that I would encourage to look.
Yeah, I would take a look at this. There's definitely new information. So maybe it would, give you some idea of the structure of the gluon. So the
solitonic models, non-soliton models are, one of the models that people consider it, and they actually map this experimental data on that model, which was fitted very nicely.
Okay.
But the fit, of course, it's not guaranteed that model is correct, because it was just linear fit. So
okay.
Not to,
So the recent thing that we are discussing is that how does it work for heavy ion collision? So in the medium, what happened? So when you go beyond that, so the structure would enter, but then indirectly. So it may be another test for the theory. Yeah. But thanks for the information.
Okay, do you have any other question? So he will be here until the coming Tuesday.
Yeah.
Probably.
Yeah.
On Wednesday,
On Wednesday, I leave. Yes. Yeah.
So if you have any, if you want to have some discussion,